Math 8, Unit 6, Pythagorean Theorem in Real Numbers, Lesson 4, Part 1, Number Sets, Rational and Irrational Numbers. Okay, first, need to understand that there are two types of real numbers. Numbers that can be written as fractions and numbers that cannot be written as fractions. Numbers that can be written as fractions include decimals that terminate, like 19.67, and 3.14, which is a good approximation for pi, but isn't actually pi. 41 can be written as a fraction. It's a decimal that terminates. It also includes repeating decimals, like 0.27 repeating, which is actually 3/11ths, 0.3 repeating, which is a third, 0.2050505, which I don't remember what that is as a fraction, but since it repeats, it will be a fraction. Also the square root of 100, because the square root of 100 equals 10. Irrational numbers, or numbers not able to be written as a fraction, would include the square roots of numbers that are not perfect squares, like the square root of 61 and the square root of 2. A number like pi. And a decimal that goes on forever without repeating. Now this one does have a pattern, it's just not a repeating pattern. 0.10100100001, and then after that it would have 4 zeros and then a 1 and then 5 zeros and a 1, etc. So our number types, we've got the first numbers we've started using as a species, as humans, would be the natural numbers, the counting numbers. 1, 2, 3, 4, 5 on up, where you have objects and you're trying to see how many you have. You just point at them and start counting with the natural numbers. The next set of numbers just adds 1 to its list, and that is the number 0. These are called the whole numbers. And we've been using them since about 725 AD, so only for about the last 1300 years. A major advance to mathematics with the number 0 is actually our place value system. Next we move on to the integers, which you first learned in 6th grade, and you really got very familiar with them in 7th grade. And they include the negative numbers, and those have been used for the past few hundred years as well. Before that, you could try to solve a problem and come up with a negative answer. You would say no solution. But we've come to make sense of negatives. It allows you to indicate you are lacking something rather than having it. If you're dealing with height, a negative could represent below the ground level. If you're dealing with money, a negative could represent debt. Then we move on to the rational numbers. These are prehistoric because they're just basically your fractions. We use the letter Q to represent rational numbers because Q stands for quotient. Quotient's the answer to a division problem, and this includes all answers to all division problems. We use N for natural, it's a bolded N, W for whole, these are just nice quick abbreviations, and Z for integer. The thing about Z being integer is that keep in mind that English is not the only language that math was developed in. In another language, integer does start with Z. And another thing, I gets used for something else. Now, these are all the rational numbers. Now, the irrational numbers is a separate set. This is the set of all numbers that are not expressible as an integer fraction. Things like square roots, pi, and decimals that do not repeat or terminate. Now, if you looked up the definition of irrational number, an irrational number is a number that can be written as a rational number is a number that can be written as a ratio of two integers. An irrational number cannot be written as a ratio of two integers. The square root of any whole number that is not a perfect square is irrational. The cube root of any integer that is not a perfect cube is also irrational. The decimal form of an irrational number neither terminates nor repeats. It goes on forever without repeating. So here's the set of real numbers, kind of in a Venn diagram form. We classify real numbers into many different sets. These sets each contain numbers and some sets include numbers from other sets. The Venn diagram below shows the relationship between these different number sets. What I want you to notice here is that the natural numbers, represented by this rectangle in red, are completely contained within the rational numbers, which would be this rectangle in blue. And also integers are completely inside the rational numbers. Whole numbers are completely inside the integers, etc. But over here, the irrational numbers are completely disjoint from the rational numbers. There is no overlap. Okay, let's go ahead and classify some numbers by telling what sets they belong to. Now, square root of 16 actually equals 4. So, because it is equal to 4, it is a counting number, so it is natural. It's also a whole number. It's an integer. And it is a rational number. Now, we can use those abbreviations from before. I'm going to go ahead and write those here. Remember that the abbreviation for natural is a bolded N. The abbreviation for whole is a bolded W. Integer is a bolded Z. And rational is a bolded Q. And I'll be using those abbreviations on the next problems. Okay, example 2 is a 0. Now, 0 is a whole number. It's not natural. It's not one we use for counting with. It's an integer, and it is also rational. 13/51. Well, since it is a fraction made out of integers, the top number 13 and the bottom number 51 are both integers, it is rational. Now, it does not reduce to a whole number, so it is rational only. 0.12 repeating is a repeating decimal, making it an integer. It can be written as a fraction. In fact, it would be not 4/11. Maybe I shouldn't have tried this. 4/33, I do believe. Okay. 16.3523498. Because it terminates, it is rational. If it had gone on forever, then it wouldn't be rational. There isn't an apparent pattern, but it can be written as a fraction: 16 and 3,523,498 10 millionths, which could reduce, of course. Example 6, 53.9355634, etc. Well, that one keeps going on forever, according to the ellipsis at the end, so I'm going to call it irrational. And then square root of 13, it's between 3 and 4, but since it's the square root of a non-perfect square, it is itself irrational. Now, the pi plus 1, if you take an irrational number and add a rational number to it, it's going to stay irrational because there's nothing about the 1 that's going to get rid of all of those extra decimals. So pi plus 1 is an irrational number. Okay, I know that a number is rational if it can be written as a fraction. Its decimal form either terminates or repeats. And I know a number is irrational if it cannot be written as a fraction, or its decimal form does not terminate nor repeat. This is the end of the first lesson. Please watch the second video for the rest of the lesson.